When recapping the ring, you'll recall that one of the tricky things was trying to figure out where the magnetic field pointed from one of these current elements that makes up the ring carrying a current I. It was easier to show this in class because I had something three-dimensional, the bicycle wheel, and I could kind of demonstrate with string and fingers and so on. You'll recall that there were several components of the cross product shown here, that canceled when you took into account all the different IDSs on the ring. What you end up with is only magnetic field components that point in the X direction. That can be shown fairly easily if you're good with the right-hand rule. You can start doing a whole bunch of right-hand rules and see that all the components cancel out from your various right-hand rulinesses except for the negative X component. If you're more of a mathematical person, here's an example of how you can show the current element in the front of the loop and the back of the loop would end up having only negative I components, and their K components would cancel out. So I'm going to skip right to saying that we can calculate the X component of this current element only, and bear in mind that the cross product, although it would technically give you a almost 360-degree angle between IDS and R, this angle theta only differs from that true angle in that the signs would have opposite SIGN signs. So I'm just going to sort of take it for granted that we're dealing with a negative X component and just not mess with the directionality stuff too much. That leaves us with this extra sine theta component, and we just have to start rewriting some things until we have a whole bunch of constants that we recognize. If I give the ring the usual capital R radius, then we end up with the following relationship. These are the usual trigonometric substitutions we can make. This is just the Pythagorean theorem with red R vector as hypotenuse. These are just the usual trig substitutions. I wrote that as a straight up Pythagorean theorem, but if you look at the diagram for a minute, you'll see that the thing that I've labeled as y here is truly the radius r of the ring. So this becomes square root of x squared plus capital R squared. And sine theta is r over r. That leaves us with a bunch of constants. R, of course, is the fixed radius of the ring. X is the distance along the x-axis to our point of interest P. And for all of these current elements, X doesn't change either. The only thing left in here that'll be integrated is ds. Now, ds is just all the little segments that the ring is made up of. So when I integrate all of them by summation, that just gives you the circumference of the ring. This whole part then is just 2 pi r. That leaves our final answer as mu naught I times r squared over 2 times x squared plus capital R squared to the 3/2. And remember, this was the X component. I didn't take into account that there was a negative sign from the cross product here. So this would give you a negative in the I hat direction. And that's just kind of a nice reminder that the magnetic field for this ring points through the middle of it. At the risk of ruining my pretty drawing up here, you have field that points through, and off axis it starts to get a little bit loopy, fringy. In other words, this thing still has the appearance of bar magnet field lines if you kind of step back and think about it for a minute. So everything is kind of as you might expect.